Okay, hi everybody. My name's Sebastian Scherer. I'm an associate research professor at the Robotics Institute at CMU, and I wanted to give you a little bit of a background on kind of why we went down this route of creating this data set for this challenge. And kind of give you a little bit of context, and then eventually we'll go and talk more about the details, how we made this challenge, and the data set itself, and the creation metrics and so on. Okay, I think a lot of you know, real-world imagery is challenging and noisy. And so I just want to kind of give you some examples of the kinds of problems that we're interested in looking at, and then some kind of more philosophical thoughts maybe that might bring up some discussion. So one of the problems that we are working on right now is the DARPA Subterranean Challenge. And so this is underground, having a team of robots trying to find objects as accurately as possible. So it's really, it's a lot about SLAM, because you have to localize these objects, and you only get a point if you're accurate enough. At CMU, together with Oregon State University, with Team Explorer running in this challenge. The part that's kind of very relevant here is this problem of degraded sensing. So these environments we're in, the typical environments are tunnels, urban environments like subway stations, power plants, and then caves are kind of the three types of environments. And they're not necessarily lit. Sometimes they're lights, sometimes there are no lights. There are fog, dust, lots of challenges in these systems, and you have to make SLAM, and you have to make SLAM robust enough that you trust your robots to run autonomously with it. So our approach right now it consists of two sets of robots: a ground robot, three ground robots. You see one of them here in the picture. That have a custom perception payload and some communications nodes that drop, and then a custom drone that's optimized for flying indoors, also with a perception payload on board. And of course, one of the things we would like to do is to remove the heavy LiDAR on top. I think that would be very desirable. But and there is a lot of effort underway for this, but for now we're stuck with what systems that work reliable. Just to give you an idea of the kinds of environments we're testing in, so here's another of our ground robots climbing upstairs, and then here's a quick video to just kind of show you what this kind of challenge looks like. So the beginning is from August last year was the tunnel circuit. So this is kind of how it looks like inside. So you can see there's lots of specular reflection from the water, dim light, some fog from condensation. So here's kind of our ground robot going inside the tunnel. Here's the drone. You can see it actually kicks up quite a dust cloud as well, and it's flying inside. Then here's some of the fog that DARPA has set up, and this can get quite thick. Something else you can notice here is there's a lot of kind of dust particles that reflect off. And then this is now from February in the urban circuit. So the drone actually takes off from the back of the ground robot, all fully autonomous. And then here it descends down into a shaft, and then explores the bottom level. You can see, there's there's no light here. This is dark, so it's a pretty challenging SLAM problem as well, in addition to the other challenges. Now, something. Oops. YouTube. So something, some other kind of example of a problem we're looking at is, for example, for bridge inspection, and so this is inside of a bridge, and here is very dim light. And you can see actually the picture is pretty blurry because of motion blur, and so that actually causes lots of problems when you want to try to do 3D reconstruction. And in particular, what we are really going for is one of millimeter level reconstruction of large structures with cameras. So it's particularly we're looking at a lot of stereo data here, and we've been able to get quite good results, but it's a challenging problem because as the image noise goes up, a lot of these algorithms start to fail. And just kind of like a last example of problems that we're interested in is, this is now a little old, but I think still relevant, was for example to detect fires inside a ship. Mute this. So this is flying inside the ship using some cameras, downward pointing cameras, forward-looking RGBD sensors. Everything's on board here. This is now 6 years ago, and so there's the ship's on fire, so there's visual images are not very good, but are present. And so we tested this, for example, with oil fire, wood fire, and also we also have a thermal camera on board here, but in this particular example, we're not using that thermal camera. But those are, since our research area focuses a lot on flying, of course, cameras are very desirable because they, in terms of the size and weight, if you exclude the computation, they're very small. So just kind of to give some context here, I think if you look at visual SLAM methods right now, they have a lot of potential, but the success for autonomous systems has been a bit limited. And I think that comes down to part of it is just due to a lack of data sets, and I think that was kind of what drove this. In some sense, if you're doing any, and part of it has been also a shift in terms of methods towards learning-based methods. So if you look at UROC and Kitty data sets, these data sets are very popular, but if you develop a system and only train and test on these data sets, you're really doing the community a disservice, because these data sets are not broad enough that they're really and diverse enough that they really exercise these methods with these large number of parameters well. And the other part that kind of brings out is that it's very easy to measure accuracy, and so a lot of SLAM research has kind of focused on, we're more accurate than this and more accurate than this method, but it really comes down to often robustness. And for autonomous systems, you might be more willing to accept drift and less accuracy for a more robust solution. And so maybe so just to kind of highlight this, right? So I think this is this is where a lot of research is on, okay, how accurate can we be? But actually, for autonomy, this other axis is probably more important. And so this kind of led us to try to design this challenge and put forward this data set to really kind of push and get a good sense of methods, try to include some things like weather and other degradation to make it a more relevant challenge than the kind of data sets that are very popular right now. So we have a total of $5,000 in prize money, thanks to Microsoft, and then Wenxuan will tell you a lot more. And I hope will convince you to participate in the challenge. You know, I think it will be quite exciting, and we're really curious to see what these kind of different methods trade-offs are, and if you can really kind of get some of these methods out. So, for example, Daniel mentioned this D3VO. I think will be very interesting to see how that will perform on the challenge data set, for example. Okay, should I hand over to you, Wenxuan?
Okay, thank you, Dusty. So let me share my screen here. Okay. Sorry. Okay. So my name is Wenxuan Wang. I'm a project scientist in Carnegie Mellon University. I'm going to introduce this SLAM challenge in the CVPR 2020 workshop. So this challenge is a joint work of the Air Lab at CMU and the Area Informatics and Robotics Group at Microsoft Research. In particular, I would like to thank all my colleagues, Carlone Zhu, Xiangwei Wang, Yaoyu Hu, Yuhen Qiu for the great work, and the supervisors Ashish Kapoor and Sebastian Scherer for the tremendous support. Our challenge is about the visual SLAM in challenging environments, as Basti just mentioned. So we have a monocular track and a stereo track. So each track contains 16 trajectories, which consist of 8 easy trajectories and 8 hard trajectories, respectively. So this is an ongoing event. The deadline will be on August 15th, which is 2 months away. Please check out our workshop website for detailed information. So as Basti just mentioned, the motivation behind this challenge is to push the limits of the current visual SLAM algorithms in challenging scenarios with degraded sensing. We hope to utilize this challenge to first identify the limitations of the current visual SLAM algorithms, and secondly, overcome these limitations. So how can we do this? First, let's take a look at some of the most popular benchmarks for visual SLAM. These datasets have been around for many years, during which they really push forward visual SLAM research by providing practical testing cases, standard evaluation metrics, and so on. However, each of these benchmarks only covers 1 or 2 types of scenes. For example, the Kitty dataset only contains data collected in the driving scene. The data in Europe is collected in a machine hall and a room environment. And the TUM RGBD dataset is collected in office environment. Besides, they provide relatively small number of data from the perspective of deep learning area. If you look at the motion patterns, they are constrained by the data collection setup. As you can see in at the bottom, we did a principal component analysis on the camera motions. The figure shows the three principal components of the translation and rotation motion respectively. The data from KT has one dominant axis in both translation and rotation, because we know that the vehicle is mostly moving straight forward combined with small left and right turns, which is like a 2D motion. The U-log is collected by a UAV, which is obviously would have less pitch and roll motion. Although the TUM RGBD dataset is collected by a handheld camera, it still shows large motion bias. So we argue that the lack of motion diversity has two limitations. First, the simple motion is insufficient for evaluating a visual SLAM algorithm. I'll show some experiments later to demonstrate why motion patterns is important for the evaluation. Second, learning-based algorithms trained on these data cannot generalize to other tasks with different motion patterns and will become biased. Therefore, we'd like to create a benchmark with diverse testing scenarios, with challenging scenes and diverse motion patterns. So, as we can imagine, collecting real-world data and ground truth labels is very expensive. It often relies on an elaborate sensor setup and careful calibration. The ground truth of the SLAM task usually comes from other high accuracy sensors such as LiDAR, GPS, or motion capture system. As I mentioned, the data distribution is often constrained by the physical property of the hardware. With recent advance in computer graphics, many synthetic data sets have been proposed. We also take advantage of this. We utilize the photorealistic simulation environment AirSim, which is developed by Ashish and his group. The simulation provides reliable ground truth labels with very low cost. However, one biggest issue is known as sim-to-real gap, which means the algorithm's performance will drop when transferred from simulation to the real world due to distribution difference. How can we overcome this problem? Our solution is large size and diversity. So this idea is borrowed from the successful story of domain randomization, namely increasing the diversity of the environment. The model learned in simulation could be easily transferred to the real world. In our TartanAir dataset and the testing cases in this challenge, we set up diverse scenes, including urban, rural, domestic, public, and sci-fi. Our dataset contains a large number of label data, which is an order of magnitude larger than the existing dataset. Besides, we lose the motion constraint, which results in an unbiased motion pattern. The spatial focus of this challenge is in challenging things, such as changing light conditions, low illumination, reflections, adverse weather, dynamic objects, and so on. Here are more examples of scenes in this challenge, including day-night changes, low illumination and the changing of light, bad weather, such as rain and storm, and moving objects, like machinery and fish and bubbles. So, well, can we really identify the limitation of visual SLAM algorithms use these synthetic data? So we tested ORB monocular and ORB stereo algorithms on the 8 hard trajectories in this challenge. ATE, KT metric are commonly 3 common metrics for the visual SLAM algorithms. We can see the arrow on the ATE and KT metric is very large. But we found these three metrics are less distinguishable in our case because the algorithm often lose tracking of the camera poses. So we show another metric called valid rate, which means the percentage of frames that have valid pose estimation. So this evaluate more towards the robustness instead of accuracy. Under this metric, the monocular algorithm only have 50% valid rate, and the stereo algorithm is more robust, over 70% valid rate. As a comparison here, we also show the performance of ORB stereo algorithms on KT dataset. We can see a huge gap, which indicate how they are suffering in our data. Okay, we found many interesting failure cases. The figure shows where the ORB monocular lose tracking. Typical reasons are getting close to an object, moving objects, illumination change, dynamic object in the scene, in this case, a falling leaf, and reflections. In the stereo cases, it's more robust to moving objects and illumination changes. We found many failures are caused by lack of features, also the reflections and moving close to an object. We've spent many efforts setting up the challenging scenes. So the next question is, are these challenging features really matters for the visual SLAM? So we did this experiment. We turned off the challenging features and collect the data along the same trajectory in the environments as the video shows here. So as we can see from the table, by adding the storm and changing from a day scene to a night scene, the performance of both monocular and stereo methods drops significantly. At last, we show how the algorithm performs with respect to different motion patterns. We set up 3 levels of difficulties. In the easy setting, we only have translation and raw rotation. In the medium setting, we use 6DOF slow motion, and hard setting has a 6DOF fast motion. The experiments show that the motion pattern has a huge impact on the performance of all the 3 methods we tested. The successful rate dropped significantly and constantly with the increasing of difficulty of the motion patterns. Now, let's move on to the harder question. How can we overcome the limitations? As I mentioned, using simulation, we can provide multi-modal reliable ground truth labels. If you go to our website, you can download all these data, including RGBD stereo image, depth image, segmentation, optical flow, and camera poses. This allows people to explore many research directions, such as SLAM based on the semantic information or multi-modal SLAM. Obviously, people can also explore learning-based methods, since we provide all of these data as a training set. In our preliminary experiments, we trained a simple neural network for the visual odometry task on our large training data. Then, without any fine-tuning, we directly tested the model on the KT dataset. As shown in the green line, the network outputs reasonable results without seeing any of the real-world data in the training time. Our simple model even outperformed ORB monocular without loop closure, which suffers from a big scale drifting problem. At last, I'd like to talk about the hard work behind this challenge. In order to enable data collection in this large scale, we developed an automatic pipeline. First, we implement a frontier-based method algorithm which can automatically calculate the next exploration location. So the frontiers are shown as a blue peak here. So we use RT star planning algorithm to calculate the collision-free trajectory, which guides the exploration in the free space. So then we sample the nodes and edges in the free space, and the nodes and edges are stored in a graph data structure. Then we sample the trajectories from the graph. In the data collection process, we randomize the incremental distance and angles along the trajectory. The poses are then sent to a virtual camera in the simulation, and we record all the data. After we get the raw data, we then calculate the ground truth optical flow by image warping. We also calculate a mask for the occlusion and dynamic objects. At last, we verify the data to make sure the data are synchronized and eliminate missing frames or bad data such as large occlusion. So as a summary, this challenge aims to set up a benchmark for challenging scenes. It provides large amount of training data with multi-modal labels. So we hope this challenge could push forward the visual SLAM research, and we welcome both learning-based methods and non-learning-based methods to participate in this challenge. Again, this is information of this challenge. I hope I can see you in the award ceremony. Okay. Thanks everybody for the attention.
Yeah, so there's 2 more months until the deadline. The deadline's August 15th at midnight.
Yes. Yeah, there's 2 months away. Okay. Is there any questions from the audience?
So I think we have a couple of questions in the Google Doc. So I think one of them is about the tunnel exploration. So how do we evaluate which one's better? I mean, the metric for how do we evaluate if it's better to have 2 versus 1 robot for the tunnel? And so it's really the time limitation. So we have 1 hour to find as many objects as possible. And having more robots allows you to cover more space, since the space is a couple of kilometers long. Next question is, which kinds of perturbations are particularly hard to be robust to? What types of perturbations where we may be close to breakthroughs? Wenchen, do you want to take this question?
Mm-hmm. As we showed in the slides, so we found that our finding is kind of consistent with a lot of research, review research. They report their difficulties in the visual SLAM algorithms, like lack of features. Like if you're moving too fast and if you are very close to an object, then the scene changes a lot, and it makes the visual SLAM suffer. And also for the dynamic objects, if it took large part of the field of view, then it definitely will be a very hard question, a very hard issue. We also found those storm and rains be added to the scene also create a lot of difficulties. Okay. Right.
I can read the next one. Maybe you can answer that one too. So how do you define if pose estimation is valid compared to absolute ground truth or pose changes?
So we trying to eliminate multiple multiple types of invalid cases, like if there's some error in synchronization, then so basically we do this by warping the image using the optical flow. We calculate the optical flow is calculated based on the camera pose and the depth image. Then we warp the right image to the left image using this optical flow. So that's basically include all the data raw data we collected from the simulation. So if everything is okay, so when you look at the photometric error, that will tend to be low. Yeah. So we will eliminate the unsynchronized image, and sometimes there's missing frames. Also, there will be occlusion, or sometimes the camera goes into an object, will cause some big occlusion, and we will delete those data from our data set. Okay, so I guess that's all for the questions.
Okay, also there's one okay question on the IMU data. Yeah, so IMU, we're working on adding the IMU simulation. And there are some more things that we're potentially adding in the future. And then maybe one thing that might be good, Venture, is if you could just show the website, maybe quickly, the AI Crowd website.
The AI Crowd, right?
Yeah. So right now the data set has about 400,000 images. And so trying to increase that in the future.
Yeah, if you go to aicrowd.com, so you click challenges here, you can navigate through and find our challenge here. So this is for monocular track. You click here, here's a 0 track. We've already got a lot of submissions. Yeah. Actually, I already saw some submissions that has already outperformed the ORB baseline we put there.
And then, Venture, maybe you could say a little bit about like how many environments and what environments for the evaluation are.
So we provide 16 trajectories for each track, and they all come from one different environment. So we're using very diverse scenes as this testing set in this challenge. So there are more information if you just look at the website of this workshop. There are 2 examples of the how the sequence look like. This is one scene, and this is the outdoor scene, and on the right is the indoor scene. Right. Okay. So we provide some tools for the challenge. If you go to the GitHub here, Air Cloud, you can find the what is here? Oh, what is it? Here. Okay. No.
Yes. So we have some tools for evaluating, running the data, and since the data is quite large, one of the things that we're also doing is we can have a way to use it easily in the cloud if you don't want to download, I think, what is it, like 3 terabytes of data. You can just use the data in the cloud.
Right. Here's the GitHub repository for the how you can download and show, display, visualize those data. Yeah, I think it's quite easy. You can also put issues like or questions here. Right. Okay. Then there's no more questions.
There's a question here. Do any of the sequences contain complete loops?
Right. When we sample the data from the environment, we always sample a loop. But in some cases, if there's a invalid data, so we just we will cut the trajectories. So we cannot guarantee every trajectory has loop, but I think most of them will end up to the starting point.